Yes, so my name is Gabriele De Chiara from Belfast. So I'll be chairing the second session, and the first speaker is Gonzalo. Gonzalo, if you want to share your screen.
Yes. Let me... Okay, can you...
Okay, so first speaker is Gonzalo Manzano from IQOQI in Vienna. We'll talk about thermodynamics of gambling demons. Gonzalo.
Okay, so thanks a lot, and I would like to thank the organizers also to give me the opportunity to talk here. I'm going to talk about the thermodynamics of gambling demons, which is a joint work with collaborators in NITheP in Trieste and at Aalto University in Helsinki. And there's some results that involve both theory and experiment, and in particular classical and quantum theory, while the experiment is only for the classical part. So let me just start with a brief introduction. So as you all know, Maxwell Demon is a famous thought experiment that was introduced by Maxwell in the 19th century, and which has been long discussed in the literature in different versions. The main idea is that a small intelligent being or demon is able to gather information about the microscopic dynamics of a thermodynamic system, and then use this in order to produce some paradoxical behavior that seems to violate the second law of thermodynamics. So here I just want to make two remarks. One is that those are only apparent violations of the second law, which are solved when considering the erasure of the information that the demon needs in order to operate, as first noticed by Bennett, using Landauer's erasure principle. And the second remark is that Maxwell Demon has been seen as a feedback controller, namely an agent that can measure the system and perform operations that depend on the outcomes of the measurement in order to operate. And for these situations, it has been shown that some modified thermodynamical laws apply, like for instance, the Clausius inequality gets a new term that takes into account the information that the demon employs in the measurement, the demon gathers in the measurement and employ for doing the feedback. Okay, so indeed, this modified thermodynamic laws has been experimentally tested in the last decade. Thanks to the great advance in the experimental techniques, there have been a lot of setups in which Maxwell Demon situation has been implemented. Just to mention a few of them, I can mention this in colloidal particles, in optical traps, electronic devices, nuclear spins using nuclear magnetic resonance spectrometry, or also circuit quantum electrodynamic setups. So as you can see, it involves both small classical systems and also quantum systems. Okay, so the main motivation of our work is to ask, okay, but what happens if the demon cannot perform feedback? This is what we call the gambling demon. It's a demon that instead of feedback can only stop the process, so decide to stop or not stop a process. And this is inspired by what happens with players in the casino that can decide to play or not play the game, but of course they cannot change the rules of the game. No? For instance, they cannot apply feedback control over a roulette. So this is essentially the situation that we want to consider. So we have an open system, which may be classical or quantum, that follows some stochastic evolution. And there is a fixed driving protocol, lambda, that drives the system in a time window that goes from 0 to tau, which is the final time. And of course, the system is open, so it can exchange heat with some external environment. And the demon is able to gather information about the system and just decide if to stop or not to stop the process. So we refer to gambling strategy to the criterion that the demon uses to stop. So when some arbitrary condition is verified for the first time, the demon decides to stop the protocol, and otherwise he continues until the end of the process. And the times at which the process is stopped are formally called stopping times. And they are, of course, a random variable because the condition may be verified at different instants of time, depending on the different realization of the process, which is stochastic. So this is kind of analogous to a gambler in a slot machine. So here, so you can see that here the demon invests some work that is represented by these silver coins in order to drive a system. So in this case, place the slot machine. And he wants to recover some free energy as from the work that he invested. So if the demon just do that until the end of the protocol at final time tau, it is bounded to lose. So because of the second law of thermodynamics, the work invested will be greater or equal than the change in free energy of the system. But our interest is to ask what happened if the demon implements some smart strategy that allows the demon to stop the process at specific smart times so that he can invert this inequality by taking the average over all the trajectories stopped at different times, at the different stopping times. So in order to ask or to handle these questions, we use Martingale theory. So Martingale processes are a set of stochastic processes that were introduced by Paul Levy in 1934. And there are stochastic processes that fulfill this nice property here, which essentially means that the average, the best estimate of the average of a process M at a time tau, given some previous observations until some instant of time t. So the best expectation is given just by the last value of the process at the last time it was observed. And this simple properties somehow has a lot of interesting consequences. And one of them is that these processes fulfill what is called this dupe optional stopping theorem that allows to link the statistics of the process at the stopping times to the statistics of the process at fixed times. And this is essentially what we need in order to handle the problem that we pose. These Martingale processes are very well known in mathematics and in finance, but they has been also only used in stochastic thermodynamics very recently. In particular, it has been shown that just a few years ago that the exponential of minus the entropy production in non-equilibrium stationary processes is a martingale. And this is, I think, a very, very nice result because it is something which is stronger than the usual fluctuation theorem. And indeed, it implies the fluctuation theorems when you take t equal to 0 in this expression. But of course, in our situation, this is no longer the case. So the exponential of minus the entropy production is no longer a martingale in more general non-stationary process like driven processes and so on. So essentially what we need to do is to kind of identify a new martingale process that is adapted to our situation in order to handle these problems. And this is essentially what we've done. So let me first present the results for the classical case that apply for the framework of stochastic thermodynamics. So we identify a new martingale that leads to this stopping times work fluctuation theorem. And of course, using Jensen's inequality, this also leads to a second law-like inequality, which are for process at the stopping time. So processes of different lengths. And as you can see here, we have some first term, which is essentially the entropy production in the setup. So W is the work, and delta F is the non-equilibrium free energy. And then we have an extra term delta, which is this term here, and which we call a stochastic distinguishability. And essentially, is a stochastic version of the distinguishability of the probability density of the process in the forward the protocol is implemented at some intermediate instant of time with respect to the the density in the time reverse process, which is the process in which you start in the final state of the forward, and then you just apply the time reverse driving protocol, which is fixed. So this is, as you can see here, if you take t equal to tau, then the densities are the same because we choose that the initial state of the backward is the final state of the forward, and this gives 0. But of course, it's not necessarily 0 at intermediate times, like the stopping times we are interested in, since the process is not reversible. So we test these results experimentally using a single electron box in the ¿Sí? ¿Sí? Oh, perdona. Sorry. So we test our results in a single electron box, which essentially it consists of a copper island coupled to 2 aluminum superconducting leads, which are coupled by thin oxide barriers that allows electrons to jump inside the island. So the island can have either 1 electron or 0 electrons, and the state of the island is monitored by a single electron transistor that allows to infer the state of the system, as you can see, for instance, in this picture here. And then there is a gate voltage that drives the system following a linear ramp until some final time tau. So the stopping strategy that we employ here is just the following. So we stop trajectories when they reach a work threshold. If they reach a work threshold before the end of the protocol, or otherwise we wait until the end of the protocol. And as you can see here we plot the average of the work minus the change in non-equilibrium free energy at the stochastic times given by this obtained by this strategy versus different values of the work threshold. And you can see here that clearly for values for small values of the work threshold, we can invert this inequality, and our results are very tightly bound by this stochastic distinguishability term. Here, the solid lines are numerical calculations, while the dots correspond to the experimental data. So we also test the stopping time fluctuation theorems. And as you can see here, the stopping time fluctuation theorem is with pretty good results. So it is very near to 1, both in the simulations and in the experiment, contrary to what happens to the usual fluctuation, to a naive extension of the usual fluctuation theorem, that in that case goes clearly over 1. Another thing that we see is that by comparing different protocols with different speed, we see that in faster protocols, we can see actually higher apparent violations of the second law than in slower protocols. And this is, of course, related to the fact that, in this case, the stochastic distinguishability will be very high, while in this case it will be close to 0 because the process is close to reversible. Okay, so now let me move to the quantum results. So essentially, what we used in order to extend our results to the quantum framework is a 2-point measurement scheme in which we kind of introduce projective measurements on the density matrix at the beginning and at the end of the process that gives some outcomes n at time 0 and n at time tau. And in the middle, we use the framework of quantum jump trajectories, meaning we consider some environmental monitoring of the system, which leads to a record R that essentially tell us the type of jumps that the dynamics that were verified on the dynamics at the specific times at which they were verified.
Gonzalo,
So,
you have 5 minutes, including questions.
Okay, thank you. I will finish very soon. So we focus in this case on stochastic entropy production, and which can be defined following, for instance, these papers here as the change in entropy of the system given in the TPM scheme, and and the stochastic heat that is exchanged with the environment during the quantum trajectories, which depends on the environmental record. And the problem, of course, of the quantum case is that we need the 2-point measurement scheme to meaningfully describe the the thermodynamic variables like the entropy, so that the problem is what happens at the intermediate instant of time. I mean, so you have to somehow decide to stop the process before you measure, but then your measurement may introduce some disturbance on in your system. And in order to handle this, what we use is a trick that we introduced in a previous paper, in which we essentially split the stochastic entropy production in 2 terms. One, which is just capturing the effect of the last measurement, and the other one that is kind of a classicalization or classicalization of the quantum stochastic entropy production, and then use this second one in order to obtain a martingale. So essentially our results in the quantum case are the main difference when we took all these things into consideration is that we get an extra term here, which is this delta S anc, which is essentially the change in entropy that is produced by the final measurement when you stop the trajectory. And then it modifies the entropic balance in the equations. And what we observe is that this quantity may be either positive or negative at the stochastic times. So it may be beneficial if it is less than 0, or if it may be detrimental if it is greater than 0. Of course, in the classical case where the stochastic evolution of the system is always in an eigenstate of the density matrix, then all these terms become the classical ones. Okay, so let me just go to the main conclusion. So we introduce a gambling demon, which stops a driven non-equilibrium thermodynamic process of stochastic times according to some gambling strategy. We derive classical and quantum fluctuation relations for work and entropy production at the stopping times. We test our classical results experimentally in a single electron box. And finally, from the quantum part, we see that the coherence in the dynamics may introduce an extra uncertainty term that can be in principle either beneficial or detrimental for the gambling. So let me just finish with a remark, which is that still these gambling demons are acquiring and processing information. And of course, the erasure of that information will restore again the second law, as happens in normal Maxwell demons. The point is that the bounds that we get from Martingale theory are usually much stricter than the ones that comes from the gathering of and deleting of the information, because we are essentially in the continuous limit in which we are performing measurements continuously. So we are gathering information continuously. So that's all. So thank you very much. And if you're interested, you can see the reference here.
Thank you. Thank you, Gonzalo. We have time for 1 or 2 questions. I cannot see on the Q&A. I cannot see questions. I have a quick question. Do you think this could be extended to cooling?
Yes, I think so. Absolutely. So our results are general for entropy production in general. So in this case, we just consider the prototypical situation in which you just have one thermal bath and the driving. But of course, you can consider also more situations, also quantum thermal machines or different setups. And of course, cooling as well, either driving, so cooling assisted by driving or by another flow of heat.
Because you could maybe speed up, no? So if you're not bothered by the cost, you could maybe speed up some cooling process rather than wait for the infinite thermalization.
Yeah, indeed. So yeah, like here, so here our trick was essentially that if we are spending a lot of work, then we stop the process. So you may think in something similar also for cooling, right? So if you are kind of using too much resources in order to cool, then you stop and just let thermalize, let's say. And otherwise, you continue with your process. So then you kind of filter somehow trajectories that you want to keep.
Okay. I think we have to move on. Thanks a lot, Gonzalo, for a nice talk.